All right, welcome to Monday, I guess. Hope you're having a good Monday. Maybe every Monday should be on Thursday. Make it easier. I don't know. Today, we're gonna continue with trees, and specifically, we're gonna continue with binary trees. So kind of from now on, the trees that we talk of will mostly be binary trees. Okay, and we're gonna go into some details about these that shows why we like binary trees a lot. Okay, so we will go into that. Any questions before I get going? Don't forget to go to labs tonight. Again, if you haven't either done lab 2, because some people hadn't handed in lab 2, and I turned that off, so you have to email me and tell me why. And lab 3, which is this week, if you need some extra time to do it, please try to get it done by Sunday. And Sunday is also when our homework 3 is due, and let's see, that's about it. I have my office hours this evening from like 7 till 9. I will try to do them in the lab, so I'll just kind of be flying around the lab. I may plant myself in one place and people can come to me instead of doing the whole Halligan helper thing, but either way I'll be in the lab. Questions? Okay, so what is we're going to do today? UNIX tip of the day, they're binary trees. We're going to talk more about these ideas of postfix, infix, prefix, etc. Then we're going to go into these cool things called binary search trees. Okay, binary search trees are really the reason we like trees so much. And we'll talk about a whole bunch of functions you can do on binary search trees. Okay, and if we get to it, we'll talk about sets. But you'll actually do a little practice. Remember that I said binary trees are ripe for recursion. So we'll actually practice some of that at the end of the class. Recursion using binary trees. Okay? All right, let me show. So most of the UNIX tips of the day are kind of like a little, utilitarian and kind of boring. Let me show you kind of a fun one. Does that sound okay? If you log into the homework server, there is a program on there which I put on there. It doesn't come. It comes on many flavors of UNIX, but it happened. I had to install it specially. But comp 15. Let's see. Public cowsay, and then let's have it say I don't know. I'm a cow. And then you type that in, and it says, right? And it says, oh, look, I'm a cow, right? And you can have it say anything. You could say, let's see. All right? And it'll do that. You can also have it. You can have it say, let's see. Let's say. Let's see. Not saying this out loud, like that. And instead of cow say, we can say cow think. And it's got little deep bubbles, right, like that. What's even neater though is that there's a whole list of, let's see, is it there? No, hang on. ls/comp15 public cowsay. Whoops, decided to die on me. Hold on. Hello. Yep. Cowsay share. Cowsay. There we go. There's a whole bunch of different ones you can try. Anybody have one they want to try? I heard Hello Kitty first. So hold on. Cowsay. Hang on. Cowsay -f. What was it? Hello Kitty. And then I don't know. Meow. Well, right? What's another one you want to try? How about Stegosaurus? Stegosaurus. I have no idea what a Stegosaurus would actually say. Stegosaur. Oops. I think my internet connection is really terrible right now. Is that how you spell Stegosaurus? If it keeps going on me here. Hello, internet. Come on. Come on, you're ruining my demo. Ah, hang on. Let's try, we're on tough secure. There we go, let's try it again. Let's try it again. OK. Yeah, there we go, OK. Ah, this is really bad. I'm trying, I'm really trying. Thanks, Tufts Internet. Hold on, there we go. No. Cow say, what did we want to do, dash F, Stegosaurus? A-U-R-U-S? What does the Stegosaurus say? I don't know. Maybe. How about this? And some of you will get this. Some of you will get this if it doesn't. There we go. Oh, you can't see it. Right? That's a pretty good one. A Stegosaurus with a top hat. Who knew? Hang on. One more. Let's see. I'll do one more. Which one? Vader. We'll do Vader. Vader. Whoops. Hang on. Vader koala. OK, hold on. OK, I got it. We'll do Vader first. Vader. I don't know. May the force not be with you. Whatever, right? That's pretty good, right? OK, so anyway, feel free to play around with those. There are lots and lots of those. OK, so that's cow say. You can have that come up as your default login, too, and it can say, you know, how are you doing or whatever. All right, there's another one. So there's one that's built into the Mac. It's slightly different. You just say, and then you can say, like, may the force be with you.
May the force be with you.
Right, and it actually speaks to you, right? And this is really great when you know your girlfriend's SSH password, and she's sitting across the room, and you say something like, you know, you've been working a bit hard. Why don't you take a break?
You've been working a bit
and
hard. Why don't you take
and she goes, oh, my computer's telling me to take a break. And then you laugh. So anyway, you can do that. So those are a couple of fun little ones that you can play around with. OK? And have fun with those. All right. So let's see. So that was the Unix tip of the day. Cow say and say in OS 10. It tells you how to do it if you forgot. Oh, I guess I could have just. I forgot that Let's see. Let's see if it lets me in quickly here. Comp 15 public file. No, public cow say all cow files. This will do all of them. So you can actually see all of them and whatever. Right. The Ghostbusters is pretty good. Right? Let's see, flaming sheep, elephant inside an ASCII snake. There's a jumbo, one little jumbo. Dragon's pretty cool. So anyway, you can check out those. All right. Oops. There we go. OK. So let's get back to binary trees. Now, this is what we covered at the end of class yesterday. We basically did a whole example, but just to review, if you have a tree like this, and it happens to be a binary tree, and you want to represent operands, like arithmetic operands that have operators that have two operands, A and B, you can do it with a binary tree because the left-hand side and the right-hand side are the children of the asterisks here. Okay, and this is A times B. If we want to print out, if you didn't want to print out the postfix notation, which is what we wanted to do the other day, you can actually do this, and you can actually print it out with full parentheses. Okay, and remember, postfix is nice because no parentheses are necessary. If you do this form, which is called infix form, in other words, the operator is between the two operands, you actually need all those parentheses. You don't necessarily need the inner parentheses, but you definitely need some outer parentheses, because otherwise your rules of operation wouldn't work correctly. Okay, but here's how we could do this. Okay? If our node is null, just return. right? And this is, again, this is a nice recursive on here, right? Print a left parentheses, first thing you do, right? And then you just call in order on the left child. And remember how it's recursive, so it will keep calling lefts and keep printing a bunch of parentheses, okay? And then when it returns from printing all the left children down the whole tree, you'll print the symbol. And then you do in order right child, and it will go down the other side of the tree and print that one. And then you print a right parentheses. And if you do that, you'll get all these different parentheses in here. You'll get a outer one, then you'll get another inner one for every symbol. And then you'll get another outer one at the end of each one, right? And that'll actually be a legitimate, if your tree is correct, legitimate infix way of representing this. Again, pretty simple, all things considered. It's like 6 or 7 lines. Zoe.
When you say if the node is null, do you mean if that node doesn't have any children? Or
No, it actually means if you try. So B right is null because there is no children there. So that's the one that's no children. It's not that if the it's not if but if the node is right. I think you're correct in what I think I misunderstood. If you call this on B right, B right will be null, so you'll get into this and you'll go, oh, it's null. So you're doing more calls than necessary, right? You could probably change this if you wanted to say if left child is null or is not null, call in order. I guess it's kind of the same idea. Okay, yeah. All right, other questions on that? Okay, so that's how we would do infix notation. We could do it with fewer parentheses if we wanted to. This is the one where we just say, look, if the node's null, return. If the node has a left child, and this is kind of what Zoe was asking, right? If the node has a left child, print a left parenthesis. And then go ahead and do the left child. If it doesn't have a left child, why print a parenthesis? There's no point, right? And the same thing, if the node has a right, only if the node has a right child do you need to print another parenthesis on there. Okay? All right, any questions on those? Okay, so that was the in order traversal. And what does this one represent in an in order way? Let's just walk through the algorithm here, just a little bit. We don't need to do the whole thing, right? What did it say to do first? I might not remember. Right? Let's see. Yeah, first thing is print. If it's not null, print a left parenthesis, then do in order, then print the symbol, then do in order right, then print a right parenthesis. Right? So first thing we do, it's not null, so we're going to print a left parenthesis. OK, and then we do what? If you don't remember, that's all right. It's a go left. So we're going to do here, and then what are we going to do here? Check if it's null. If it isn't null, well, yeah, if it's not null, we return. If it is null, we return. If it's not null, we do a left parenthesis. So you need another parenthesis there. And then we go left, right? And then this one, same thing. If it's not null, we do what? Print a left parenthesis. Oop. And then it can't go left and right. So it's going to try to go left, and then it's going to print A, right? And then it's going to say, I forget what the exact thing was. Then it's going to say print a right parenthesis. Yeah? Like that. OK? And then it's going to return. And right after it goes left, it prints the symbol again. And then it goes right. And this one, we have to do a left parenthesis. And then we go left. And this one, we have to do a left parenthesis. And then we end up printing B. Another right parenthesis, return here. And then the symbol. And then go right, and then can't go left, can't go right, print the symbol. Whoops, forgot the parentheses there. And it's going to be like that, and then you're going to go back here, print a left parenthesis, et cetera, left parenthesis, et cetera, et cetera, et cetera. And it will do it does a lot of work, but that will actually work. OK? Let's see if that's right. There we go. Yep, all those parentheses in there. OK? And that would work based on the arithmetic rules. If this tree was, you needed the arithmetic rules. OK? Yes, question? Which represent? This, some arithmetic, it represents some number A plus B times, well, actually, B times C first, then A plus A, et cetera. It's just if we put numbers in here, we'd be able to use it as a calculator, or at least to print out all the numbers in this form, right? And again, by the way, the reason we have, I don't know if you ever thought about this when you're in like 3rd grade, But the reason we have order of operations is so that we don't have to do lots of parentheses. Right? You have to do many fewer parentheses with order of operations. Because you just know, oh, I have to do this one first, so I don't need the extra parentheses. Okay? It's kind of nice. OK. All right, that was in-order traversal. This is the same one without all the extra parentheses. It's kind of nice. And you can kind of see what's going on. You know that you have to do b times c first, and then you're going to do a plus this whole thing. So that's why we would need the parentheses around there. Right? Well, if you knew order of operations, you wouldn't necessarily, but OK. All right. OK. We can also do post-order traversal, which is what we did yesterday, postfix. And this was a real easy one, right? Get left, or post-order left, post-order right, and then print out the symbol afterwards. Pretty simple, and no parentheses necessary. OK? Lots of animations you can go to on this stuff, too. OK, I'll show you some others later. But there's lots of good animations that you can have on this. OK, pretty easy. All right, post-order traversal leads to postfix. And again, post-order traversal means you basically go left, go right, then print. So go left, go left, go left, right, print. So this gets printed first, and then it comes back up here, but it has to go right, then it has to go left, then this one gets printed, it has to go back. But before it prints this one, it has to go here and print this one. You see that it's basically the order going this way. And we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like that. Okay? So you'll see this in a little bit, actually, why this one's an important one later, too. Okay? All right. So there's lots of other types of traversals. There's pre-order traversal, which means print first, then go left, then go right. Okay? Print first, then go left, go right. There's also, I mentioned this one yesterday, there's also level order traversal. This one's a little harder to do. Okay? All the other ones we've talked about, you can actually use a stack to do it. Why can you use a stack to do it? Because you can just basically push onto the stack, and everything needs to come out in last in, first out order. Okay? For a level traversal, you can't do this with a stack-based solution. Like, there's no way to actually go about doing it. Right? Because you need to do this one, and then you do this one, and you're doing it by level. So it's like this whole level, then this whole level, then this whole level. But if you traverse down here, there's no way to get back over here and then back over to this one through this recursive method. Okay, I urge you to try it, but you'll get frustrated, I think, right? Because it's really not easy to do. What you can do, though, and since we're on queues, we might as well walk through this one. You can use a queue to actually do this. Okay, let's think about this, see if we can figure this out. Okay, front and back of our queue, like this. OK, here's how this actually works. All right, and you'll do this in lab on next week actually. OK, so what it does is first thing you do is you push on, or well, I guess you in queue the first operator here. OK, you know what the next thing you do is? Guess. Well, move back. Yeah, thank you. That besides doing your queue operations correctly, what's the next thing we would do to this algorithm? Any ideas? Like, just throw one out. Yeah. In queue the children. Good idea. It's incorrect, but it's a good idea. What you actually do is you dequeue. And you go, why did we push that on there or why did we put it on there to begin with? Because you need to start this out somehow. And this is like, once you in queue something, then you start like a while loop. And you've got something in the queue. Otherwise, you would be done. So what we do is we dequeue from the queue, OK, and we print it out. OK, so we dequeue and we print it out. And then front is now going to be over here. And there's nothing in the queue. But now you in-queue the children, which is what you said. Now you in-queue the two children. We in-queue plus and then asterisks. OK, and we're done with that. But then the while loop starts. So what do you think we do? Dequeue. And my back is all messed up here, right? Not my literal back. It's OK. But there. So you dequeue this one, and you print it. right? And then, all right, and then what do you think you do for this one once you've printed it? NQ its children, which in this case are A and asterisk. And we're done, but now we're back in this while loop again. We DQ again, right? So we DQ this one. And back is now over here somewhere, because I'm a little hard to do like in real time, right? And you DQ this one, print it, and then NQ its children, which were, let's see, that was this one. So you NQ its children, which are plus and G. Plus, and I guess we could do this circularly, but I'm not going to right now. G, back is now over here, right? And you can, and then you now DQ. So let's see, we just did this one. Now we're going to DQ A, and then NQ its children. You see how this is working now? Look what we've done. Plus plus asterisk A. The next one that's going to DQ is the asterisk here, and then we NQ its children, and it actually works just fine. Okay, question?
What's the test for your while loop? You keep saying that we're entering a while loop.
What do you think? What do we normally test for our while loop? And you've been doing this all week on your homework assignment. Yeah. Check if the queue's empty. And so you keep dequeuing until, if we dequeue and there's no children, there's nothing that's going to get inqueued. So eventually this will exhaust the queue, and everything will get printed out just fine. Does that make sense? Yeah. So you can use this queue method to do this. Okay, and if that didn't make sense, go back and watch the video, and hopefully you'll be able to figure it out. But basically, NQ this one, DQ this one, and now we're inside some while loop. DQ, print, NQ its children. DQ, print, NQ its children. DQ, print, NQ its children. DQ, print, no children. DQ, print, NQ its children. See how it's working? No? Yeah, so you can see how it works, but you can't really do this recursively. That's why you need the queue to do it. Okay, questions on that? Okay, all right. Now let's get into these things called binary search trees. And I've been saying for like days now that this is really why we care about binary trees. We care about them because of things like you can set up arithmetic with them, right? But what's really neat is when you get into these things called binary search trees. What do you think we're going to do with binary search trees? Search, woo, right? Binary search trees are used in searching, right? Because we've given it more information, and you can do the searches very quickly. Okay? Here's what a binary search tree is. Okay? For every node, all the items in the left subtree are smaller than the node, and all the items in the right subtree are larger than the node. Okay? We have a term for what we're describing here in general. What I'm describing is the invariant of a binary search tree. In other words, for a tree to be a binary search tree, for a binary tree to be a binary search tree, it has to meet this requirement. Okay, so we say that this thing called the invariant is the requirement to make it a binary search tree. Okay, I'll use this word a lot during the semester, right? That the invariant is what we have to always keep in mind when we're making these data structures, because if the invariant is broken, we either need to fix it or it doesn't make our structure anymore. It's not correct. Okay? I'll mention that a whole bunch of times. Okay? For every node x, all the items in the left tree are smaller, and all the items in the right tree are larger. Let's see. This is a binary search tree because 2 is less than 6, and 1 is less than 2, and 4 is greater than 6, but it's also, 4 is greater than 2, but less than 6, because it's in the left subtree of 6. And how about 3? 3 is less than 4, but greater than 2, because 3 is in the right subtree of 2, so these all have to be bigger than 2. Make sense? Okay. Somebody say, whoa. Yeah, it's kind of neat. This is not, why isn't this one a binary search tree?
7.
What's wrong with 7? It's bigger than 4, bigger than 2, less than 6, right? So So this is not a binary search tree. This has broken the invariant, which says that everything to the left of 6 better be smaller than 6. OK? So this is not a binary search tree. OK, pretty simple on that idea, I think. Sorry. I'm sorry? Well, for a binary search tree, it's whatever node you're at. Everything to the left has to be smaller. Everything, no matter where in that side tree it is and that subtree it is. Everything to the right has to be bigger. Right? And if you look, you go, OK, 6. This is good because 8's bigger than 6. Good because 2 is smaller. Good because 1's smaller than 2. Good because 4's bigger than 2 and less than 6. 3 is smaller than 4, bigger than 2, less than 6. 7, bigger than 4, good. Bigger than 2, good. Not less than 6. So this is not a binary search tree. See how that works? Yeah. It's a little tricky looking through these and kind of seeing it real quick, but you won't. It's not like I'm going to ask you that. OK? All right. Question?
What do you do with duplicate numbers?
Good question. Doesn't really matter. Doesn't really matter what you do with duplicate. If you're inserting them into a binary search tree, duplicates don't really matter in the big picture. Many times what we will do is we will say no duplicates allowed. If you find a duplicate, don't just enter it again. If you do want to count duplicates, all you need to do is keep a count as well as the actual object in there and say, how many of these do I have? And so you can keep, like, there could be 6 2s in this, like that. Your next homework assignment is going to be on binary search trees. And you will have to do duplicates, but we will use the method of keeping extra information in the node. OK? Question? It would just be another field in the struct. Yep, absolutely. It would be the count. And most of the counts would be 0 until you add 1, and then it's 1. Right? And exactly for the homework assignment, we're actually going to, when this gets printed out, it'll actually print a little asterisk saying, hey, there's more than one of these. But it could be any more, one or more, basically. OK? Any other questions on binary search trees in general? Yeah?
Instead of the 4 on the right one, there was a 7. Like the 7 wouldn't be to the right of the 6, would that still be illegal?
Technically, it is still to the left of 6. Because remember, this whole thing is to the left of 6. OK, that means because 6 is, how do you get there from 6? You go left from 6 to this whole subtree. Right? So that's what you have to think of, the whole subtree.
So then why isn't the right one a binary search tree?
Because of this 7. So 6, everything to the left of 6 has to be bigger than 6, or less than 6. Right? So all of these have to be less than 6. And that one's not, so breaks the invariant, not a binary search tree. OK? Good questions. All right. And it does take a little time to get this, but you'll find that this stuff's not too bad to pick up. OK? All right. What can you do with binary search trees? Well, first of all, what's nice about binary search trees, right? On average, the height of the binary search tree, right, or depth, whichever you want to call it, is going to be log n. And remember, when we talk about log behavior and log n, we like that. Right? We really, really like log behavior because it's fast. Because, for instance, the log base 2 of 1024 is 10. In other words, if you have 1024 things, to find one, if we're going to do a search, and if we only have to search logarithmically, will take you 10 searches. Right? 1024 gets down to 10 just because it's logarithmic. 2048 goes down to only 11. Right? You double it, you only have to do one more search. OK? Which is very cool. On average, we have log n. OK? Because logarithms grow slowly. It's great. OK? This is why we had these things. OK? All right. So a lot of people ask, is a tree a data structure or an abstract data type? My answer is not what you want to hear. It's kind of like, oh, it's a little bit of both. It is a data structure in that it's got nodes, and it's built a node-based structure. But it also has functions associated with it. You can have all these functions in some other structure. But this is, in a binary search tree, these are the ones we're going to care about. So I won't ask you, is it a abstract data type or a data structure? Because I would accept either answer. Right? Yes, Kate. OK, sure. So an abstract data type is a definition of a bunch of functions or methods for an underlying structure. And I don't care how the underlying structure is built. Okay, so in this sense, we could say, oh, look, we can find min, we can find max, we can say if the thing contains it. We could define those. So that's basically the interface, if you want to call it that. The actual data structure is the underlying structure, for lack of a better term, of how it's actually built. So is it using a linked list, which is a data structure? A bunch of nodes one after the other. Is it using an array, one contiguous piece of memory, etc.? Okay? So that's the big difference there. OK, so we're going to define a bunch of methods here. Let's just go over some of these. In fact, I don't even think we need to go to the other slides where it's written out, because I think we can figure this out. OK? Given the binary search tree structure, okay, think of a way to find the minimum and find the maximum. In fact, do this. Talk to your neighbor about this and see how you would actually do this. It's not hard. Shouldn't take you that long. OK, I think that was enough time. Who thinks they have an idea? Somebody from this side of the room. OK, go ahead. Go ahead, Camille. For find min, go left, go left, go left, go left. Right? So let's think of a while loop to do this. If I pass in find min of some node n, what's it going to be? And it should be, let's say, int in this case. What's it going to be? What are we going to do for this one? Camille, you said it, so you're going to go left, right? So how about this? If what? What would our base case be here? Yeah. Say if n's left is null. If n left equals null, what are we going to do? So you're going to return, let's do it this way, return n data. Something like that. OK? And then what are we going to do? If n does have a left, what do we do? Find min n left. Wouldn't that do it? It's going to check and see. OK, does 6 have a left? It does. Find min left. Does 2 have a left? Yes. Find min left. Does 1 have a left? No. Return 1, return 1, return 1. So I forgot one thing on here. What did I forget? Would have gotten a compiler warning at least. Yeah, return find min n left. OK? Because it's got to return. This one returns 1. Boom, 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 and 1 is the answer. OK, so I don't want to insult your intelligence, but find max is pretty simple. What's find max going to be? Exactly the same thing, except if n right is null, return n data, return find max n right. OK, good. Yeah, question. Yuki. Can't be 0. Why could that be 0? Why does that break our invariant? 0 is not bigger than 2. Yep. Yep. So as long as you have a legitimate binary search tree, this will work. Good. OK. How about contains? Can we rewrite our function here to do contains? Let's see. It would be, let's erase the whole thing here. It would be bool, because we want to know just if it contains it. Bool contains. OK. And then we're going to have to pass two things in, right? We would have to pass in, let's say, node n and int, say, I don't know, we'll call it int I. Okay. How would we do this one? Yeah. Andy.
If in I equals m arrow data,
If I equals node data, return true. Okay.
if in I is greater than
Good. This is actually key. If I is greater than node data, how's that sound? What are we going to do?
with the right.
Say again.
Color function contains
Oh yeah, contains
node right.
node right, comma, I. Yep. Okay, and then otherwise, what are we going to return?
Return
Sorry, my board's running out of space. Can return contains. Okay, and sorry, contains node, or is it n? Sorry, n. Been writing this wrong. No, n left, comma I, and then what else? Yeah.
Wouldn't that statement have to be in an if statement for I is less than node data?
Yeah, this one does have to be in the statement, right? Because otherwise, you're going to never have a base case of true here, right? So let's do that. If I is less than node data, right? Return contains, and then what else are we going to do at the end? Yeah, return false, right? Okay, would that work? Yeah.
Wouldn't you like run the risk of passing it a null?
Yeah, we do have a couple different. We do have a little problem here, right? So if you end up calling left and it doesn't exist, then this would have a seg fault, right? So you could do a couple different. You could solve this a couple different ways. What's an easy way? Yeah. Add another condition in our if statement. Okay, which would be what? Oh, okay. You could add two statements, right? You could say if I is less than node data and I left is not equal to null, and you could do the other one. There's another just one liner we could do up for a base case. Yeah.
You can move return false to the top. If it's null, then return false.
Yeah, you could do that. If it's null, then if, let's see, node data, if not node data, we could just say that, return false. Probably not the best way to do it. We probably should use the if node data equals null. But null and false are kind of the same thing in this case. But yeah, so there's a couple different ways to actually simplify this. Yeah? Don't you just, you have to return something. If n data, if not n data, or if n data equals null, we have to return false. Right? Because you have to return a Boolean value. Yeah, good. Yep. Daria.
For the one where I is less than node data,
Yeah.
why is that one return contains less than the other one?
It should be. This should be return contains. That should be. You're absolutely right. This one should be return. Sorry, this is like terrible, like looks terrible on the board. I'll show you a good one in a second. Adam.
Do you need that second return false?
Do you need which second return false?
The one underneath that.
Underneath here?
Yeah.
Let's see. OK, so you do have to have some return false, right? If you're going to have all these if statements in there.
Right, but since you have return false as the base case of
Uh-huh.
wouldn't that
I think the problem with that would be you'd get a warning saying can't do that. Even though you know that it's going to return on every case, the compiler's not going to know that. So you're going to have to do something like that. I'll show you in a sec what the other solution is. Okay, yeah, question?
Can you just explain why the not n data works?
Yeah, okay, so, well, I probably shouldn't have done that. But in null actually equals 0. 0 equals false. So it's basically like saying if the node is equal to null, which means it's equal to false, then return, right?
By going in, like it seems like you're going into the data of a null.
Oh, very good point. That's actually a very good point. You are actually, yeah, that shouldn't have been n data. Thank you for, why didn't anybody else catch that? Did you catch it? If not, you could just say if not n in that case. Yeah, good call, good catch. Or if n if n equals null, would be fine. Yes. So is this what you were saying? You can take out the last return statement and return false. You could do that. Yeah, if you take out the last if statement. Yeah. OK, let's take a look at some of these before we do insert, which is kind of interesting. OK, find min we already did. Start at the find max, start at the root, go left until node. Oh, I don't actually do these in C++, do I? Oops. OK, well, does the tree contain x? If t is empty, return false. OK, that's what we did. Basically, if the node does not exist, or if node is null, then return false. OK, if it is x, return true. That's what we have here. OK. Recursively call either t left or t right, depending on x's relationship to t. OK, that's all we do for that one. Contains. Now, before we go any farther, what's the asymptotic complexity going to be for contains? What do you think it's going to be? On average, let's say. Or, yeah, I guess we generally don't talk too much about averages, but let's say it was a well-formed binary tree. Yeah. Logarithmic, right? Because basically you're splitting the problem in half, aren't you? Right? Just like we did with the sorted array, we're basically splitting it more or less in half. Now, in this case, it's not half because 6 doesn't happen to be right in the middle of our whole tree. But in general, you're going to do that. What's the worst case behavior? N, if we had one of those degenerate trees, which was like boom, 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 all in one line, you have to go through all n nodes before you get to the one you're looking for, possibly. Okay? So as long as we have a relatively well-formed tree, asymptotic behavior is going to be logarithmic, right? Next week we'll talk about how do we keep trees more or less regular like that. Okay? All right, that was contains. Insert. Go ahead and think through insert with your neighbors, if you haven't done that yet. Go ahead and think through insert. Who has an idea? Coming from this side of the room. Go ahead. What do you think? No? Somebody else have an idea of how we're going to do the insert? Yeah, go ahead.
So if the number is less than the node, then you're going to insert on the
Okay, if the node is less, insert on the left. If it's greater, insert on the right. But that will get you most of the way there. But again, we run into this problem. What do you do? How do you end the whole thing? Yes, I think you've got it. I think we've got to be a little more concrete about it. But yeah, that's exactly right. So basically, you say, look, start at the whatever node you're at. Check the one. Let's say we're inserting 7. Is 7 less than 6? No. Is 7 greater than 6? Yes. So we insert where? Node right, right? And then we say, OK, is you might want to check if it's null or not, right? Well, first of all, you say, is 7 less than 8? Is 7 less than 8? Yes. So you would insert left, right? And then now there is no node there. So you have to be a little careful. You have to say, instead of insert, you first would want to check, does the node to the left exist? If it doesn't, guess where 7 goes? Boop, right there, right? And isn't that the only place on this tree where 7 can legitimately go right now? Right there. Make sense? Okay, yeah.
We should also check if it's equal.
Well, it depends. For this one, I'm not going to worry about if it's equal. But yeah, in some cases, you would want to check if it's equal, and then you'd have to update the count or whatever. But otherwise, if you pick less than or greater than, it doesn't matter which side they go on. It doesn't actually matter. Okay? All right. So let's insert another one into this one. Let's insert, let's see, 5. OK, 5 is good. Let's start up here. Start at 6. Is 5 less than 6? Yes, go left. Is 5 less than 2? No. Is 5 greater than 2? Yes. I should say, does the right exist? Yes. OK, so you go right. Is 5 less than 4? No. Is 5 greater than 4? Yes. So does the right exist? No. That's where it goes. See how it works? And we've retained a binary search tree. Yes?
Will there ever be a situation where you're not adding on to like the end of the tree?
Will there ever be a situation where you're not adding on to the end of the tree? Let's see. Can you give me, no, there won't be. Can you give me an example of where you would think it might happen?
Well, like if you had to put something between the 2 and the 4 or something. And
Yeah, let's say we put something between the 2 and the 4. Let's pick something that goes between the 2 and the 4. 2.5. That work? OK, 2.5 is less than 6. 2.5 is greater than 2. 2.5 is less than 4. 2.5 is less than 3. 2.5 goes right here. Right? Yeah, there's no way to there's no need to split in that case. Yeah?
So using the problem of, say, of identical numbers,
Yeah.
would we just, if we were trying to insert an identical number, would we say, it wouldn't be efficient to ask if it's contained, so we have to go through the entire thing again.
Right. You wouldn't need to ask if it's contained. You just basically, you'd add a condition. If it's equal, then update the count. Or just say if it's less than, go left, else go right. And it will always put the same ones to the right. But we don't really care if we're not caring about which way it goes. OK? Good. Yeah, Jenny? Well, that's kind of the question. Duplicates, we generally either don't care if it's left or right. Could be either. We pick one and go with it. Or we update the count of this. So we have another field in the struct that says there's a however many 8s there are. And you would just keep it. You wouldn't insert anything. You'd just update the count. Make sense? OK. Good. Yes?
If the 8 was the root of the 3,
If the 8 was the OK.
how would things change? Would it be correct?
Say again. Well, I'm not sure exactly what you mean. If the 8 was the root of the tree. So there's an 8. What's going to be to the left of 8? 6. And then what? And then what's up here? So it would be 2, and then 4, and then 3, and then 1. And what are we trying to insert?
No, like, would it be different, like the operation?
No, it would be exactly the same. Right? Because you'd say, if we're inserting 7, is 7 less than 8? It is. So it goes here. Is it less than 6? No. Does 6's right exist? No. So it goes right there.
No, like, is it like less efficient?
Is it, say again? Oh, is it less efficient? Yeah, it would be less efficient. Yeah, which is why we try to keep trees fairly well balanced, as we call it. OK? Yeah, good question. Yes? Yeah, so you've gotten to the heart of the matter. When you build a tree, how do you make sure it's balanced? There are various tricks for doing that. We will talk about some of those next week. There's actually a number of different types of trees. There's one called a red-black tree, which we won't talk about, but you'll learn about in algorithms class. There's what's called an AVL tree, which is what we will talk about in class. And there's some other ones that keep things relatively balanced. Yeah, we'll get to that. Good question. Hold off till next week. All right? Other questions on this? OK. All right, so similar to contains, right? We have to check lefts and rights. If t is empty, insert at the root. We forgot about that part, but that's all right. If t is equal to the x, special case, this is where we could maybe keep duplicates. Okay? Or just recursively call t left or t right, depending on x's relationship. Right? And if the node traversed is null, then we insert there. OK? Questions on that? OK, guess what? Now we get to, now remember what I said back here. I said there are some easy ones. Find min, find max, contains, insert. And then I say there's a hard one. Now, hard is not like difficult in the sense of like once you know how to do it, it's not hard. It's just trying to trick you to figure out. I want you guys to try, let's see, figuring out remove. How would we do a remove, say, 4, or remove 7, or remove 6 in this binary search tree? Talk about it for a couple minutes. OK, I'll give you guys like 5 minutes to think this through. And then we'll come up with some answers, and we'll see what we can do. Okay? This one's a tricky one. How's it going? Yeah, that's what we have to figure out.
I figure you'd have to pull it off and then get the other way. There may be a better way to do it.
Yeah, think about it. Think about how you might do it.
I have a question
Yeah.
about the last thing that you put up there. You
Sure.
said if you pass it a null pointer, then you insert there, right?
You would want to check for a null because you can't, like a linked list, you can't go backwards, right? There's no way to like go backwards to the previous one. Although I suppose returning you could get back, but then it would just get a little bit fuzzy. Yeah, good question.
We feel like we have a terrible solution.
What's your terrible solution?
Okay, so get to the point that you are looking for. So let's
Sure.
say it's 2,
OK.
and you're going to get rid of 2.
OK.
So create an array, a dynamic array, potentially.
Uh-huh.
Take all of the things to the left of 2, and then all down, and put that into the array one by one. And then take all the things to the right of 2, go down, et cetera,
Uh-huh.
and put that into the array one by one.
OK. Put them all into the array. OK.
Delete every 2 and everything underneath it.
OK.
Start back at the one above it. If there's nothing above it, I guess it's the beginning. But
Uh-huh.
start back at the one above it.
And then insert everybody?
Build it again.
OK. That would probably work. It wouldn't be that efficient. I'll
That's
tell you
why
that
we
right
think
now.
it's a
But yeah,
terrible
good,
solution.
good. Yeah, no, that's all right. That's all right. Good. You guys think you have something?
Yeah.
Think you got something? What do you have?
So we're saying if, well, if there's just like, if the thing is a weak, just like take it off. Or if there's like,
Yeah, go ahead.
If it's like, if it's something with a bunch of branches, you put the right one where it was, and then take the left branch and put it on the very left leaf.
OK. So how would you remove 2?
So it put like, so make 6 go point straight to 4, and then move 1 onto the 3.
OK, can you clarify that to make it an algorithm that works all the time? Think about it for a sec. All right, yeah, think about it. How you guys doing? Think you got something?
Would you just do, so let's say you're trying to remove something in the middle.
Uh-huh.
Have its right child point to its left child.
In the middle, you mean like 2? Let's say we're trying to remove 2 from that top one.
So for 2,
Yeah.
have 4 point to 1. Remove 2, have 6 point to 4. Have 6 is left point to 4.
Okay, and what do you do with 3?
Well, 3 and 5 are just connected to 4.
No 5. Let's do the top one up there. Okay, right, but what happens to 1?
Oh, that's right, it's a binary.
Yeah, it's got to be a binary search tree. How are you guys doing?
I think we have a pretty satisfactory solution.
Okay.
Assuming that what you're trying to remove has both a left and a right.
Okay.
Because if it has only one or the other, then it's like the thing before what you're removing just has to point to whatever child it has, and then you're done.
Okay.
And if it doesn't, then you need to basically save the thing that points to the thing you're removing, go in it and to the right, and then as far to the left as possible, and then set that thing's left equal to the thing you're trying to remove's
Okay,
left.
okay. Oh, I like that. Okay, I like that.
And then you just set that equal to the original pointer and delete the
Okay, I like that. I think that would work all right. Good job. I think it would work right. Okay. Let's see. So I heard a number of answers. On this. Now, first things first. Is there always one solution for this type of tree, right? Okay, what would be somebody over here, I forget who it was, said that the easiest one to remove is which one? A leaf. Why is a leaf easiest to remove? Because there's nothing to do, right? You basically take the leaf out and you're done, right? Okay, so that's easy. That's easy enough to do. So there's case 1, leaves, right? That's easy. What's a second case? Let's say in this case we were removing something that only had 1 child. What could we do? Like, let's say we were removing 4 from the top one there. Yeah?
The parent now only has to point to the child instead of the old one.
Yeah. So don't you just, for the one that has 1 child, wouldn't you just bypass the one there by basically making 2 point to 3 on the right? 2's right now points to 3, and you delete 4. And there's nothing else we need to worry about, right? The third solution is the tricky one, right? The third one is if you're removing one that has 2 children, because then all of a sudden you're like, now what do? I've got too many things going on here. If I want to remove 2 from this, then we have a problem. Okay, give me a couple ideas that you have. I heard definitely some that would work. What do you think, Yuki? So okay, let me write this. Let me try to follow along here. 6, 8. I'm not going to have 7 in there. I'm not going to have 5 in there yet. And that's that. Okay, so we're removing 2. You're saying, well, first you have to find it, right? Like you have to basically find it. But okay, let's say you've got it. Then what are you going to do? You're going to have 6 do what? So on the same, like whichever way it is, right? Okay, so 6 is going to point to which one? 4? And then what?
And then you're going to call it an insert function and try to insert the left child of whatever you deleted.
Okay, so whatever you delete, so the left child of whatever you deleted goes in here. That would go here. And then what? I think you're on the right track. I think you've got some of the right ideas in there, but it's going to get a little bit harder to describe in a few words, right? What do you think, way in the back?
The thing is that the removing 2 is going to be less than everything to the right of 2, 4, and 3.
This is going to be less than everything to the right of 2. I agree.
So what you do is you can move 4 to the place where 2 is, and then anything under 2 to the left of 2.
So like this again, 4 to there, and then
Keeping all the references on 4.
okay.
And then you move all the left of 2 to the farthest left.
And then you move all the left of 2 to the left of here like that. Oh, okay, I guess that would work. I'm not sure it's going to be the most efficient way, but I guess that would work. What do you think?
Seems simpler to move the 1 up to 2.
Move the, OK, hold on.
6 points to 1.
Like that, OK.
And 1 now has a right child
And
4. And 4 keeps each child.
like that.
Yeah.
OK, so what if this had something like 1.5? What would you do?
They can keep that child.
Can keep that child. And,
Child gets 4.
and its child. OK, all right. Now, but we're getting a little like, oh, we got to do something that's a little bit trickier, right? OK, 2 more answers, and then we'll go to, I think one group actually had it, so I'll let them answer. Go. What do you think?
You could remove that entire branch.
Which branch?
Just start with 2 and remove 2 and everything that is attached to 2, and then go through that separate tree and recursively just insert everything else out of that tree.
That's going to take a while, though. I think you could probably do that. But again, you're going to have to do like insert, 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 which is probably doable. By the way, many of these solutions will work, but I'm not sure that's necessarily the most efficient. What did you think up there?
You get forest child and then remove it and
Get forest child, remove it, and try to place, so put 3 there.
yeah, then you have the 1 4.
And then the 1 goes there, and the 4 goes there. Can you quantify that a little bit? Almost. I think you're getting there. I think you're getting there. Hey, Jacqueline, your group had it. Do you want to explain what you guys had? I think you had this.
Basically, what you do is you traverse the node that you're trying to delete, as well as saving the node before it.
OK. Well, OK, yeah, we've got to do this so we can insert there. Yeah, OK.
So you're trying to delete 2. So you have the pointer from 6 to 2.
Yep.
And you want to set, basically you go to the right, and then as far down the left from the right child as possible.
What would we call on 2's right child? What function would we call?
Least.
Yeah, find min. How about that? Find min of the right. I like that. And then what do we do?
And then we set that one left.
Which is exactly what you were saying up there. That one, OK, goes here. OK, and then what?
Does that count? I thought you set that one least to point left toward what you're trying to delete left child.
To what you're trying to delete left child.
Right, and then you'd want to tell 6 to point to the right child originally, and then just get rid of that.
6 to point to right child's original. Right. Well, that's pretty much what you're going to do. You're going to end up, well, what's it going to end up looking like? Like that? Or is that not what you were thinking? Not sure. Tell you what. Let's look. I think you got it. It's clarifying this is a little bit trickier, right? So here's all the possibilities that we were talking about, right? We said if the node is a leaf, just delete it. That's easy. Okay? If the node has 1 child, we do this bypass business. Okay? Okay, if we delete 4 in this case, let's see. Okay. Let's see. Oops. I guess we'll delete. I guess we will delete 2 children. Here we go. If we want to delete, let's say, well, I don't know which one, 2 in this case, I guess. Okay. I don't know why I have a different one here. Replace the one we're deleting with the smallest in the right subtree. Okay, which is exactly what you were saying, I think. I believe that's what you were saying. Replace what we are removing. Replace the one we're removing with the smallest data in the right subtree. Okay, the smallest data in the right subtree. So in this case, all right, which one we're going to go 6, and then instead of the one we're removing, don't bother moving any other nodes. We don't actually need to move any other nodes. We just need to replace that data, which is kind of cool. All right, we replace that data with the smallest in the right subtree, which is find min. In this case, it would be what if we're removing 2? 3, right? And then what do you have to do to 3? What do we guarantee is true about 3? If it's the minimum, of the right subtree, what does that guarantee that it is? Smaller than everybody else, which means what about its two children? It can't be anything on its left, right? Doesn't the minimum, didn't we say to find minimum we go all the way to the left and then there's no more, all the way to the left and there's no more lefts, right? So doesn't it make sense that if we're removing 2 and we go find min on 5, we have to get to one that only has one node, one child at the most. So far, so good? How do we remove 3? It's an easy one, right? Bypass it. Okay, so this is why this is actually kind of clever. There are other solutions. You could actually do the exact opposite. You could say find the greatest of the left subtree if you wanted to. But do that. Yeah. Yes, I'll explain it. I'll explain it in 1 sec. Or I'll explain it right here. Whoops, no I won't. I'll explain it right here. Okay, first of all, you find the one you want to remove. Okay, now you're going to have to keep the parent as well because you're going to have to, it's just like a linked list. You do have to, like you're going to need the left of the parent, or the left or right of the parent, whichever one you're at. You find the one you're going to remove. And then you say, if it is a leaf, just remove it. If it has one child, bypass it, which is easy to do. If we were removing 3, we'd bypass 3 by saying 5's left gets 3's right, because it's only got one child. Okay? If you've got one like 2, where you have to have both children, here's what you do. You go to the right child of 2, which we know exists because we just said it has 2 children. And then you go all the way to the left. So you find minimum. So you find the minimum of 5. We are guaranteed, if that's the minimum, that it has no left children. Okay, because it's the minimum. They can't have a left children, otherwise the left child would be the least. Right? So because that has a minimum, we can easily bypass this one. That's a nice, easy call. All you have to do is bypass this one. And all you need to do is put 3 here. And if you put this one here, isn't it true that everything to the right of whatever's here has to be bigger? And if we put 3 there, it means that definitely everything is bigger because it was the minimum. Right? That's true. And if we put 3 here, everything to the left is still smaller than everything over here. So this one is still going to be bigger than everything on the left. 5 then jumps, 5's left now gets 3's right, which is a recursive, easy call. It's an easy one to do. Okay? Yeah?
So you're calling remove recursively.
You're calling remove recursively. Yep.
In this case, you only had to, you removed one and then changed the pointers of another. Is there ever going to be a situation when you might have to do that?
No, you'll never have to do that more than once. That's the cool part about it, right? Because of this algorithm we just came up with. It's easy to remove a leaf because you just remove it, right? What you would do is basically say, if the one we're removing is the right child, and that right child has no children, remove it. 3's right gets null. Done, right? Delete node, okay? And then et cetera. And then you could do, if it's one child, you go, OK, you've got to bypass it. You've got to go 5's left points to 4. Done. If it's 2 children, you have to go, OK, hold on. Go to the right of my node and find the minimum. So find min on this one. That's this one. Replace the data up here, and then bypass that, which is easy to do. And it'll always work. OK? Yeah? So 3 won't be the smallest, so you'd find whatever the smallest is, and whatever that one would go up here. No, well, right. That when you find smallest, it could either be a leaf or it could be only have a right child. And that's why this works. Okay? Again, think of it this way. Whatever the left child of the right, or whatever the minimum of the right subtree is, has to be bigger than this, and it has to be less than everybody else in its own tree, because it's the minimum. Okay? Walk through that. You'll see when you walk through this again, when you think about this for a little bit, you'll start to get it. If not, come on off, SARS. We'll figure it out. OK? All right. Now, we've got about 5 minutes left. Here's what I want you to do. We're going to practice a little bit of this binary search tree recursiveness. OK? let's say that we want to find the size of the tree. In other words, how many total nodes does it have? Forget about the numbers, just how many total nodes does a binary search tree have? If we're counting this binary search tree, it's 1, 2, 3, 4, 5. How do we do this? Here's the function you're going to use. Okay? Int size, and you're given the node. Int size node asterisk node. Okay? Talk to your neighbor about how you would do that. If you get done with that one, go on to the next one and try to find the max depth. That makes sense? Did you guys get that? If you didn't, that's OK. This is a real easy recursive one. If the node's null, return 0 because there's no nodes. Otherwise, return 1 plus the size of the left plus the size of the right. Ta-da! Right, and it'll work out. 6. Let's see. It's not null, so we're going to return 1 plus the size of the left. Size of the left, this one's not null. We're going to return 1 plus the size of the left, 1. So this returns, let's see. It returns 1 plus the size of the left. So this returns 1. This returns 1 plus the size of the right, which is 1. So this returns 3. This returns 1 plus the 3. So that returns 4, well, plus the size of the right, which is 1, 5. Kind of neat how that works. Yeah? Would it be exponential? No, it would be n, I think, order n, because it goes through everybody. Yep. It is, but it's not calling. It is returning two things, but remember, the binary search tree only has two things, number one. And number two, you'll always degenerate into eventually getting nulls. And it's not like you're that's a good idea. But basically, if you think about it, you're only ever calling all the nodes once. You're never recalling any other nodes. That's kind of the big thing. Okay, good. All right, I'll just quickly show you the other ones if you want. Let's see. Did I open them? No. Open tree solutions. Here we go. Sorry, I didn't give you more time on these. We'll do the mirror one later. That's the size one. Max depth is an interesting one. Max depth says first you compute the left depth. How do you compute the left depth? You actually find the depth of the left. Then you compute the right depth. And then whichever one's bigger, that's the one you want to return +1, because that's the one that's going to be the bigger one, which is what we're trying to find out. Otherwise, return the other one +1. It's kind of neat. Okay. Questions on that? I'll let you do the other one on your own. This one, which is kind of this one's pretty neat. The print tree is a neat one. Print tree is the one that, this is the one that's increasing order. That's just in order, right? It's going to be 1, 2, 3, 4, 5. That one's an in order traversal. That's why it's called in order. And then this one's a challenging one. Change the tree so the roles of the left and the right are swapped. not going to be a binary search tree anymore, but you're going to swap it. So this is a mirror image of this one. Okay, I'll let you guys try that one on your own. All right, any questions? Okay, I'll see you guys Monday or in lab or at office hours.